So just begin with welcome again to our forum today. So from my side, it's our pleasure to welcome Professor Dr. Navonil Mustafee for his valuable time for the session today that is entitled Hybrid Modeling and Simulation for Transdisciplinary Science. And we are really looking forward, Navonil, to your input today. And before I hand over to you, I would like to just give a brief introduction to your profile. I know that we can talk longer, but I will try to make it short. So Dr. Mustafee is a professor at the University of Exeter Business School. And he was also a director of research department for last 5 years. And now his research focus is on modeling and simulation, and especially he is interested on hybrid simulation and modeling approach. He has PhD in information system and computing, and also a master's in distributed system. And he has contributed immense amount of research and projects, not only in UK, rather also internationally in for the community of operation management and simulation. He is also an active participant in two large European initiatives right at this moment. One is working on working use of computer simulation and approaches in the context of circular economy. And another one is adaptation to climate change with collaboration with large interdisciplinary team international. And he's also a founder and co-founder of several international networks and community. And he's also actively organizing International Winter Simulation Conference. He also published on reputed journals, among others, Journal of Operational Research Society, Computer Operation Research, and SEM Transaction on Modeling and Computer Simulation. Navonil, you also actively take the editorial role in to the Journal of Simulation from Taylor Francis, and as a vice president, you also took role in the Society of Modeling and Simulation Internationals. And yeah, as I mentioned, that we can talk a lot about it, but today we want to hear from you, like your work and in the context of transdisciplinarity. So I will stop at this point, but also to mention another formalities, like for the audience, like feel free to write the question in the chat, although it will not be answered during the lecture. Might be better that you keep writing, and then afterwards, after the lecture, we take it for the discussion section. Yeah, so Professor Mustafee, the online floor is yours, and we are looking forward to you. Thank you.
Thank you very much, Sujit, for this very kind introduction. And thanks a lot for your invitation to present at the forum. It's a privilege to be presenting to IOER-Forum, and also I think this is a public lecture, so it is a double pleasure for me. So before I can begin, can I just say I've shared my screen. Are you able to view my screen, please?
Yes, fine.
Thank you. So good afternoon to you all. So my name is Mustafee, and I'm from the University of Exeter. So before I proceed with my presentation, I just want to say a few words about some of the logos that you see here. As Sujit kindly mentioned, I am from the University of Exeter Business School. And let me also, if possible, change the laser pointer. And the two logos you see in the bottom right is Arsino and Ultimate. Both of them are EU-funded projects. And the reason I have them here is because some of my talk is going to refer to the work that we are doing in hybrid modeling and simulation. So the outline of the talk, so in a way, I have presented the outline also in terms of my my work in the area of modeling and simulation. As Sujit mentioned, I have a PhD in applied computing. And so I look back to e-science, and then from there on, how I came into modeling and simulation and about my research. And then I'm going to talk to you about hybrid simulation, giving a case study from the Ultimate EU project. Then I talk a bit on multidisciplinary, interdisciplinary, and transdisciplinary research, and the use of hybrid modeling framework for cross-disciplinary research in the Arsino project. And then I provide a short summary. So I have, as this is a public talk, it is I have tried to present some examples, and I have reduced some technical content, but some of the slides will have the paper which I'm referring to, and which the interested delegates may like to refer to later on, or indeed ask me questions. So I start with e-science. So this is actually coming from a project. This is also a EU project. It was called Belief. And this was more than 15 years ago while I was a research fellow, and also doing my PhD before that. So basically, what we see now is that the science of this age, is becoming very ambitious, right? The problems are huge in scale, and the term e-science is now used to inform scientific inquiry, which requires non-trivial amount of computing resources, ICT elements, right? Those ICT elements could be high performance computing, high throughput computing, high speed networking, storage space, and also in some cases, access to scientific instruments. So what we see here, and there is just a conceptualization of what we may think as a user, right? Who is in a research institute, let's say like your or mine, and there is a big task to be solved. And for that task to be solved, obviously you may require input from researchers from different domains, and you are working in in a specific field, and then to work together, you need some kind of an infrastructure to work on, and that could be termed as e-infrastructure, right? E as in electronic infrastructure, and which allows the researchers to work in virtual research communities on certain problems, right? The problems could be earthquake related, particle physics related, or it could be industry applications of simulation. So what I've provided a couple of examples here. We all know about CERN's Large Hadron Collider experiments, and that is an e-science project in this term because it is collaborative scientific inquiry. There are not only physicists involved, but multiple other disciplines who are involved in these projects and having their sub-projects, but all of them obviously getting some of the simulations that are happening in the Large Hadron Collider. They work on those data, right? And in order to support this network, you have what is called as a worldwide LHC, and that is basically a grid computing, which has around 150 computing and storage sites in 35 countries. Most countries, including Germany, I'm sure, have contributed some supercomputers and storage for processing the amount of information being used, being generated by the LHC experiments, and then used by different virtual communities around it, right? Other examples from the European perspective, we know that there is the European grid infrastructure, which has superseded the EG network that we used to call it. So this is the science of of the age, right? Increasing collaboration, But here what we see with e-science projects, especially in my world, modeling and computer simulation, and I will talk to you about this in the next slides, is that it has enabled collaboration, but a lot of this is about collaboration which is supported through e-infrastructure and basically the compute element to it, right? How do you access different compute node, cluster computers, communication networks, and so on and so forth? Because the problems are so huge, you need some kind of high-speed backbone for it. So one thing which has come out of it, or used to be, right, is grid computing. Why did I say used to be? Because the term grid computing, this was very popular in year 2000 to year 2000 to, let's say, 2007 or so, before you had this cloud computing slowly taking over, right? What is grid computing? So basically, what it did was it enabled secure, controlled, flexible sharing of resources. So let's say I'm a researcher in Exeter, and I have, at the university, let's say, a HPC computer with 160 CPUs, right? But let's say my problem is really large. So I would want to collaborate with other researchers maybe, or indeed to want to secure additional CPUs, right? So this grid computing software, it had different elements to it, right? Including authentication and things like that. One example is the Globus Toolkit, an open source project, which enabled, seamless integration, right? I'm calling it seamless, but it was anything but seamless because there were digital certificates and many other things, right? And I'm talking to you about, 2002, 2004, right? So if for me to get access to compute resources, let's say in Bristol University, obviously it had to go through a lot of steps, right? Because I'm not an employee of Bristol University. So how do they know that my processing, which I am going to send over, my computations are, comes from the right party, right? But anyway, they build on open standards, and then they deliver non-trivial qualities of service. And the vision of grid computing was to, enable users to access compute, storage, and other devices, right? Just like electricity. It was called, I think, the third utility at that time. But again, cloud computing has kind of taken over. But there do remain some fundamental differences between grid computing as used in e-science applications and what we today know as cloud computing. So moving on from there, then my interest in computer simulation started from, need of an application which can use, resources such as these. Okay, I did not use 160 CPUs. I didn't have to. So my work maybe required 15, 20 CPUs. But still, for me to work on the grid computing environment, I needed a kind of a problem, right? Which was a good candidate solution for grid computing resources when the pool becomes available to you. Computer simulations, which many of you know, are basically computation models, and they could benefit from use of more resources, right? So I could see in my work, so during my PhD, that there could be strong, relationship between simulation, which is used in the industry, and which could benefit from the use of, that could benefit from the use of increased computation power, right, to run large and complex simulations. And of course, also there is a contribution from simulation in industry, because these scientific applications, a lot of them that we worked with, they were very command line driven kind of work, right? You really had to know very well what you were doing. There were no good fancy user interfaces at that time. Therefore, a lot of these e-science applications that we call was very much dependent on the developer being available, even to start the applications, because something may happen, and it's really difficult to work in that way. So here again, we are seeing maybe two different disciplines. Let's say a computer simulation being done in a manufacturing industry, right? Let's say operations researchers are involved, and to use grid computing, they are using some expertise from computer science who know about networking, the use of Globus, Condor, and other infrastructures to work together. But then here there is no assimilation of methods. It's quite, being together in a team, but the research methods themselves are not integrated. I mean, this is not what the talk is about. So we want to go a bit further to what is use of e-science in computer simulation is. Just to give us short overview of what a simulation consists of, right? So basically, the models I'm talking to you about are dynamic models, right? The dynamic models will have an element of time, right? And there are some relationship between different parts of the system, right? Let us take the example of an airport, for example, and you can think of entities as the passengers who want to take a flight. You can think of entities as the number of check-in counters, right? You can think of entities as the number of X-ray machines and the staff manning them, and so on and so forth. So there is a relationship between these entities, and the idea is to mimic reality by providing something called as a statistical distribution for these entities, right? And which could say the amount of time it takes for, let's say, a registration of a customer or check-in, right? We can say, let's say, from observation, from data, let us say that we have looked at 1,000 customers coming to the check-in, and then we can compute a distribution. Let's say, just for the sake, keep it simple, a triangular distribution. Minimum it takes 3 minutes, yeah, maximum it takes 10 minutes, and there is and the most likely is around say 5 minutes for check-in. So when you put this distribution to different elements, right, and you run the computer in faster than real time, then you can see the system evolve, right? And because it is not wall clock time we are looking at faster than real time simulation time. Therefore, we are able to then simulate a model, say 10 years, 20 years into the future, right? Or less if needed, or more if needed. And it could take anywhere between a few minutes to maybe a few hours. Therefore, once you have these models, it is very important for the decision maker because it can help them to take some informed decision. One, what if analysis, right? If there is a congestion in the check-ins, or let's say, as in the case of Heathrow Airport, there is now going to be a new runway. Then the question then becomes that to keep our KPIs of customer check-in and throughput of passengers through the airport, what should be the number of staff employed, number of check-in counters employed, constructed, in the airport or expanded. So this what if analysis is what is called as scenarios. And I will provide some examples of what a scenario is later on when I discuss the ultimate case study. It is faster than real time, as I have discussed. It is repeatable, and there is something to do with random numbers, which makes it possible to have the same results, right, of the simulation. Obviously, it is inexpensive monetarily because you are able to experiment before you are investing money into it. And yeah, experiment before you implement. So this is a very short overview of what this computer simulation approach is. And as I say, most of you probably know this, but I thought of giving a short introduction for general audience. Some examples of computer simulation that we can see. We know weather simulations are a type of computer simulation. We can think of, flight simulator, right? As an example of a computer simulation. But again, they are from different, you can see, disciplines. And you can see the use of simulations in operations research management science. So there are some examples of my work. So the first one is use of agent-based simulation to find the right place to place packages within a container because you want to maximize the use of storage space. And then there is some healthcare work looking at the patient flow in a surgery for open heart surgery cases, and then some work on 3D printing as well. But these are just examples. So one thing I would like to say here is that again, simulation, right? They're different disciplines, and I am from operations research management science or ORMS. Basically, our work is to develop quantitative models to help decision makers, mostly with operational kind of problems, like I said, airport throughput or number of beds needed in a hospital to tide off the the winter pressure, for example, right? I don't know if you have that in Germany, but in the UK, I mean, the winter pressure is something which is a really tough one, right? Many people fall sick, and obviously there are limited resources for that. So the models that I develop and I work with are mostly in ORMs, and this is not interdisciplinary, right? So when I'm talking to you now, I'm just talking about the operations research management science field, and there are different simulation techniques, discrete event simulation, agent-based modeling, system dynamics. These three are most prominent in my area, but also Monte Carlo simulations as well. Usually what used to happen is that, so before that, I think I didn't mention this life cycle of a simulation, in operations research management science kind of simulation, where you have a real world problem, like I said, number of beds you require in a hospital during the winter, or number of more staff needed to be employed because of the third runway, let us say. So there is a real problem, and that real problem could be a problem in the existing state of a system, or you are trying to plan for a future investment, let us say. And from there, you can develop conceptual models, and there are different ways of developing conceptual models. There are different methodologies of developing conceptual models as well. And then from there, you implement a computer model based on your chosen modeling technique. Then that you run some scenarios for experimentation. So scenario A, scenario B, scenario C, which is likely to be better, because you have a computer model. You are in the comfort of your home or office. You are then able to work with the stakeholders to decide on the best, what scenarios they would like it to be experimented, and that enhances the solution understanding for the decision makers, and that informs the real world problem. So successful simulation studies would have been implemented in the real world. So this is the typical life cycle of a simulation study. And traditionally, even a few years back, maybe 8 to 9 years back, most of the modeling was done using individual techniques. So, for example, agent-based simulation or agent-based social simulation. Each of these had their own journals, had their own conferences, and so on and so forth. Like you had system dynamics, right? You had the system dynamics, you have their own journal and conferences. For discrete event simulation, we have the winter simulation conferences and many other conferences, so on and so forth. But again, it became increasingly clear that these different methodologies for simulating the problem, right, to capture the problem, there were some limitations of these techniques, right, and which meant that use of only one technique for solving one problem may not be the best approach. Therefore, the researchers in our community started to work in use of integrated approaches. So how can we use agent-based system with system dynamic? Not because it's fun to use both, but to capture the real dynamics of the system in the best possible manner. Is it possible for us to combine strength and to get synergy out of the combined solution? So that was the motivation of this. And increasingly, most studies are now becoming hybrid simulation studies. But again, when we are talking about hybrid simulation studies, okay, we can talk about agent-based simulation or agent-based social simulations. There is another, community which may not be, specific to modeling and simulation, but psychology and all, they are also using social simulation models nowadays. So there is some interconnect. So just to give an example of what a hybrid simulation is, I'm just referring to one of the case studies for the ultimate project, and this is about the symbiosis of the water cycle, right? As many of you know, water is a really good resource, and in the circular economy, it has a very key element. Why? Because one, you can reuse water, because reusable water. The more you reuse water, it means the less you have to to pay to the company, right, to pump out the water, right, to switch on the tap. You can reuse the water. You can exploit energy, like when we use in heating, we use radiators, and also in industrial contexts, water is heated, and if you let the water go for treatment or to discharge without and the water has got heat, we are losing some value, right? Because it is possible to capture heat using some technologies. In the same way, it is also possible to recover materials, right? Let us take the example of a juice factory, which again I refer to the juice factory because it is also one of the cases of the ultimate case, where a juice factory, after every batch of producing juice, it has to wash down the machines, right, for new variety of juice, and then the water that is being discharged actually contains a lot of nutrients, right? So it is important to extract those. So in this work, we are motivated by the Dutch greenhouse industry, where there are two motivations for this study. One is that there is now going to be a stricter regulation towards discharge of wastewater, right? So what they mean is that the water which could be discharged from to the pumps, right, to the sewers, have to have a certain percentage, have to be even recycled further, that they to a certain level, right, and that they are referring it to as zero emission. So for that, it requires a lot of investment. And the case is that, the greenhouse farmers that we are working with, they already have their own small recycling plants. But again, in order to be able to hit this 2007 new targets, then there has to be a significant investment. So then you need to think that really, is it possible for these Dutch greenhouse farmers to work together, because they are all located, the case study we are working with in the Volt region, are located geographically in proximity. Are they able to work together to create an industrial symbiosis and develop a large wastewater treatment plant, and all of that can be water can be recycled there? That is one. The second motivation is that you can see from this figure below. This is from a different paper, by the way. That due to climate change, there's already water deficient seasons in the Devolt region, our case study region. But and you can see this graph here. Water deficit is shown in in red, and you can see the water demand in green. So there is a deficit, and which means that increasingly it is going to become difficult, and they may have to then employ water tankers to fulfill that demand. And climate change is making it difficult. Now again, industrial symbiosis is key to this, because some of the producers of producers of the Dutch greenhouse case study, they do not use the water, right? So they are happy for it to be discharged. So if you work together in an industrial symbiosis, a small farmer, rather than having to purchase water, may want to take the excess of water which is not used and bring it back to their own facility. So you are gaining strength by working together. So symbiosis decision making. So this is what I mentioned, farmers, and the question is whether we need to have a centralized wastewater treatment plant. To capture the motivations of them to join the symbiosis, we are using multi-criteria decision analysis and using it together with computer simulation. And there are 36 farmers, and obviously we have some primary data about their facilities, and also input of experts in cases where we couldn't get the primary data. The conceptual model of the Dutch case study I present here. So you can see here, I just want to refer to certain things here. And again, going back to the central theme about interdisciplinary research. So here you have agent-based modeling. There are different modules, right? MCDS is multi-criteria decision, analysis. And, why will a farmer want to join a symbiosis when they already have their treatment? And there could be different advantages for that, right? There could be the need for legal compliance, contractual conditions, so on and so forth. In the same way, there are some KPIs for the, of the wastewater treatment plant, the centralized wastewater treatment plant that we need to meet up with as well. And there are certain weights. So there is a second part of the MCDA study as well. I'll not say MCDA, but regarding to evaluate the output of the simulation. And then you have got system dynamics and all of that. It is fine. But then one thing is very interesting here. You see the use of fluid dynamics and queuing. Fluid dynamics. Now, discrete event simulation, right, is not continuous. It is discrete. For modeling the flow of water and things like that, usually we use a fluid library, right? Or continuous fluid dynamic, CFD modeling and approaches like that. But the challenge for us is that, so we are in the business school, we are trying to model the flow of water, right? What do we know about water flow? Yeah. Or evaporation. I talked about climate change, right? How much does the climate affect evaporation? Things like that. So that is not our core strength. So this project then brought together engineers from our very reputed Center for Water Systems who were working on the fluid dynamic models, right? Together with us who were working on the agent-based model, the system dynamic and MCDA element of the work. So this is again a bit more about the implementation of the Dutch case study, and which is basically showing the use of system dynamic discrete event models and also agent-based state chart. Basically, in a hybrid simulation, because it is a multi-methodology simulation, you only have one element of time, right? And these different simulation techniques, which are all imbibed in one package or one model, will use the same representation of time, but will use their underlying methodologies. And packages such as AnyLogic have made it possible. So these are representations, obviously, as you know, of the model, especially for the paper. The actual model is what I've just presented now. So let me explain a bit. I talked about the 35 farmers. So each of these nodes represent a farmer, which is an agent. You have the centralized wastewater treatment facility, which is being planned for the industrial symbiosis. Every farmer, we say greenhouse number 23 means farmer number 23, has their own processes of the fluid flow of water treatment. If I mentioned to you that they have their own water treatment plant, and also how they are using the water in their facility, right? So again, this was not possible without working with the Center for Water Systems, because we don't know much about the modeling of fluids, right? And so we have this, and then we have another agent, which is the wastewater treatment plant. And you see there are several inputs to this wastewater treatment plant and several outputs to this. Okay, this is one major wastewater treatment plant. Each of the input is for the 36 inputs from the farmers. So if the farmers decide to leave their individual recycling work and then join the symbiosis, then they will be sending water, right, to the wastewater treatment plant, where it will be recycled, and there will be a possibility for them to send the water back again to individual farmers, right? So these are the outputs going back to the different farmers if they choose to use it. I mentioned that we had several scenarios for experimentation with this hybrid simulation. As you know, we have the model, then we can experiment with different things. And some of the things that we looked is, first, our base model was with climate change and without climate change. And again, the only way we could include climate change is because we were working with engineers who knew things about water and the evaporation rate and the temperature and things like that. Otherwise, from a business school, it would have been not possible to do that. This shows, how important for this particular project, working together has been for us. And then there are different, scenarios and sub-scenarios. In some scenarios, we say all the 36 adopters join. In some scenarios, we say that only 10 adopters join from the beginning of the symbiosis, and you can allow joining later on, and they can quit as well. Why can they quit? They can quit because maybe, their KPIs that they find dynamically, as the model progresses, are not what they need. So it would be beneficial for them to actually do their individual, water processing, right? Or they may not need any water from other, givers, right, who have excess water. So things like that. So this is a dynamic model, so it will change at every time step in a way, right? Some of the things that we looked at is zero emission. Basically, when do they hit the target of zero emission? If everybody is joining, then obviously everybody is, immediately joining the symbiosis, which means that they are all sending water for recycling, and then they are hitting the target in 2023 itself. And then if there are some other cases like JQ1, which is 10 adopter joining, some allowed to leave and all, in some cases they're also missing the deadline. So 2029, the deadline was 2027. In the same way, we also have other things like tap water and alarm days. It's an example of use of scenarios for a hybrid model, and using that we can get a good representation, right? Once we run the simulation, we ran it for until 2030, and this is basically showing how much water, rainwater has been used, and how much tap water has been used. By rainwater use, it also means the recycled water, right? So the objective is to minimize the use of tap water, right? And this is for all the agents together. Number of agents joining the symbiosis, changes with time, right? And then you will see that the number of participants are changing. So these are for 5 different sub scenarios, by the way, right? And you can see that, you can make an assessment that, let's say, in this case, J16 is not probably ideal because they are using, or maybe it is the ideal one because they're using a lot more of rainwater. So this is one example of how you can see the results of the simulation. And then other things like when do people join, when they quit, these are the farmers, and total number of joined after after the end of 3rd year. So we had again 2 scenarios, one that in the join quit, they can quit after 3rd year, another one after 5 years. But anyway, I think I have spoken a lot about the ultimate project example. But now we are thinking about moving from hybrid simulation, which is still confined to a community, and thinking about what about modeling in art, engineering, and modeling and behavioral insights, for example. So we have this conceptualization here where discrete event simulation was very much about one technique, right? And one particular subdiscipline of modeling and simulation. Then we learned that, okay, hybrid simulation, again, within the simulation discipline, but you can then bring together these different system dynamic approaches, agent-based simulation, and other approaches together to create a more robust representation of the system. But can we look even further to other subject areas, arts, physics, psychology, and so on and so forth? Because there are models which are being developed by them too, right? But again, we need to combine forces together if there is a need to, not because it is only possible. That is a very important distinction I want to make. So I like this slide about multidisciplinary, interdisciplinary, and transdisciplinary science. So the first level is multidisciplinary, and which is basically 2 disciplines, which are, the output of one can be used as an input to others, right? It is about sequencing and coordination. So some of the examples of e-science that I started with are an example actually of multidisciplinary, right? So there are 2 disciplines who may have to share some, resources, and they may send some data or the output of discipline A used as an input to discipline B, and so on and so forth. Then we talk about, more interdisciplinary, where the 2 disciplines interact with each other. And this interaction is not just the interaction of researchers, right? So I can interact with a biologist, I can interact with a medical person, right? But I can develop a simulation model for a A&E facility, accident and emergency facility, and for which I will be interacting with a hospital doctor or the matron, right? But that is conversation to gain the knowledge for me, to transfer the knowledge of the operational processes from the hospital to my OR domain, right? That is not an example of interdisciplinary, because I am not using approaches which are used by by the medical doctors, right? But in interdisciplinary research, what we are saying is that, of course, it is more of interacting, linking, and blending of approaches. And then transdisciplinary, where basically both disciplines merge and maybe a new discipline is formed. So this is obviously maybe there are some problems where this would happen. But from my experience in the modeling and simulation community, and again, I'm saying this, that I cannot say for other disciplines. I can only say as an operations researchers using modeling and simulation techniques, most of the work that we are doing is still either multidisciplinary, or in some cases, it is interdisciplinary, because there are certain frameworks like the IEEE 1416 architecture for distributed simulation, which allows interaction linking of models, and different models created using totally different methodologies, right? That not known to me. But that framework, the IEEE 1516 high level architecture and the runtime infrastructure allows that. But very few models are like this. To my knowledge, I have not seen from the operation research element of a transdisciplinary research where maybe the whole new discipline has emerged with its own methods and conceptualizations and so on and so forth. So I'm using the term cross-disciplinary research to mean multi, inter, and transdisciplinary together, right? So cross-disciplinary means any of these. So what we see in the application area, so a lot of the computer simulations we do are application focused. So we have methods, right? We have methods such as agent-based modeling, system dynamics, and we have tools, right? You'll have 50, 60 different packages which can do discrete event simulation. And one reason for that is because the area is very mature. Modeling and simulation is quite a mature area. And then with those tools, you have an application. So this is the application focus area. But if we think in terms of scientific inquiry, we are thinking then about research methods, right? Qualitative, quantitative, right? And, are we testing hypotheses and things like that, right? Are we doing randomized controlled trials? So many other things. And then we are thinking of theoretical framing, and from which will emerge methods, right? So there is quite a distinction between application focus and the scientific focus. Then in this paper, which the difference in the previous one, we tried to bring together for the modeling and simulation community, what we see is an example of a multidisciplinary research. As I said, most of the research that we see are actually focusing on the tool and application. For example, application is a healthcare simulation. I go to a doctor, understand the processes of the clinic, and I use my tool. Yeah. And there is some shifting of data, of course, shifting of data. They give me some data from their, patient record system. I use it in my model. So this is an example in our community of multidisciplinary research. Then when we think of interdisciplinary methods, it is more about integration of different, interaction and integration of different modeling methods. One example is the one I gave with the Center for Water System, where you are using a fluid library together with other computer simulation approaches. So there is a integration of methods, but I must say this method is not developed by ourselves, right? So the developer of the software developed the fluid library, which allowed us to do that. Yeah. So we are not taking a credit for developing it, but yeah, what is important here is that they are working on their part of the model. We are working in our part of the model, and there is a very strong linkage in one single model. And then when we talk about transdisciplinary research, because it is the amalgamation of let's say two disciplines together, right? And which will create new theories and new research, and from which will emerge methods, tool, and applications. This is something like the holy grail, right? In our community, maybe there are examples, I don't know, but then this is the idea of transdisciplinary research. I would just give one example of work towards such kind of research, and this is to do with the RCNO project. And first, before presenting the project itself, I will present I'll try to motivate the need for this, right? So I am based in Exeter, right? And the southwest of England. And Torbay is an area which is hit by flooding. Okay, several areas which is hit by flooding. Flooding, okay, not too good, but taking into account climate change, rising sea level, what it means is that more areas will get flooded. Now, as you can see from here, it's quite populated areas. So if you are in the council, Torbay Council, you have to plan now to think 20, 30, 40, even 100 years in advance, right? You may have to shift certain populations. You may have to relocate some critical infrastructures like power substations, because if a power substation is flooded, it not only affects the power, but also it has cascading effects, right? Cascading effects of critical infrastructure failure. So where do you position them? So again, answering these questions are very important, right? And to motivate this, let me show some examples of the kind of weather, the coastal flooding, what happens here, right? These are all photos from the Torbay Council, and the slide credit goes to Mike Good, who is a partner of this project, working for the Torbay Council. They are our problem stakeholders, and you can see, the coastal flooding, and there are also, flooding of the sewers and things like that. And again, it is bringing us to the theme of water. With Arsino as well, we are working with the Center of Water Systems, and I will explain, how their models are informing our models in a bit. But before that, another key element of this project is that it is not only the engineers and operations researchers are working. We are thankful that the team also includes, it's really like I think more than 40 partners, include climate scientists who have their own kind of models. We have ecologists who have their own kinds of models, but they are all modeling, and these are all dynamic models for most cases. Now we have to bring it together, these different modeling perspectives, and this is one of the reasons we bid for this money. We wanted to integrate various modeling subdisciplines, enabling cross-disciplinary modeling of both man and nature-based systems. We wanted to focus on different paradigms and methodologies, tools and techniques, right? From these different disciplines, and how they could be galvanized together towards our 9 case studies. We have 9 case studies. The one that I showed you, the Torbay case study, is one of the 9 case studies. We have other case studies like the case study from Athens. We call it the Greece case study. And that is looking into heat waves, right? Again, the same theme, not flooding, but climate change means more heat waves, which means people who are old or maybe not living in proper accommodation and other things are more vulnerable, right? As a city council person in Athens, what can I do, right, in order to minimize their risk, things like that. So how can we deploy resources? So one thing became very clear to us is that we need a encompassing framework, right, in order to try to understand the different kinds of model being developed. So we developed this. This is very recent, actually. I mean, the work started 1.5 years ago, but the finalization of this diagram, which is basically an integration of modeling methods from different disciplines, right, which are being used in Arsino. We call it the Arsino wheel. You will see, as a side joke, you will see the colors. You see the colors of Arsino reflect the colors here. Okay, so anyway, so the idea is that it is a framework for resilience modeling and assessment, and it is a cross-disciplinary framework. It brings the modeling activities of the various sub-themes and the case studies together. It has been co-developed and it is iterative, right? This is actually the second iteration of this. Maybe it will change a little bit more. It is extensible rather than static, meaning that there could be new modeling methods which are being implemented by other cases. And we could then add to this framework. And it will also define linkages between the different models being developed, which I will come to very shortly. So at the center of this, we have tier 1, which is basically the models which are the SSP, RCP models, which have been done by the climate scientists to see the different socioeconomic pathways, and then the intended outcome, right? The carbon emission based on the choices that you make. So all our simulations at the center have this, we use this SSP-RCPs to help with the, you can think for the baseline models, those are the parameters which will be used, right? And then in tier 2, we have models which are geospatial models. We have some climate models. And again, the climate models, the output of the climate models, as many of you know, will depend upon the particular SSP-RCP case that you have chosen. So these are the first and the second tier of the model. The third tier is mostly about environmental and biophysical modeling, right? So here we have got different modeling approaches. Some models are AI/ML approaches. Some are cellular automata based models. Some hybrid models as well. Our work, mostly the business school, we are looking at mostly the tier 4, which is human and operational system models, and we are using our well-known modeling techniques, ABS, agent-based analytical mathematical modeling, so on and so forth. Because here the idea is in human and operational systems modeling, the idea is that we learn from the models which have come before us, maybe they are linked together, and then we take some decisions based on by feeding the output of those models or developing strong linkages, like I've shown with the ultimate case study, and we inform the decision maker, for example, the town planner. The last is about strategic response models, which are mostly long-term. All the models don't really have to be quantitative. So we are using system dynamic. There is also qualitative forecasting methods like use of Delphi method, choice experiments. Greece is doing some choice experiments for long-term planning, and so on and so forth. So we developed this model. This is a framework. The idea of this framework is then we have another 2.5 years to complete the project, by the way. So the framework is somewhat ready, acknowledged, and co-developed. So at least we have one point through which we have a shared vision of what everybody is going to do. And the next part of this would be to implement different models based on the context. There are also 4 other things which are supporting the framework, which is data resilience assessment, stakeholder decision making, which kind of follows some of the needs of a conceptual model. I don't want to delve too much into it. Hopefully, there will be some material available very soon on the framework development. Now I'll go back again to the Arsenal wheel for the Torbe case study. Here, because we were leading this case study, we have started a lot of work. Some of the models have been developed. Now we see the kinds of models that we are developing. So first, let me focus on tier 1, where we are using SSP1 2.6 and SSP3 7.0, right? These two are again, these are chosen by the climate scientists in our team, and all the 9 case studies will use this for their base models. We then have models such as Corfu flood impact model, and we also have a model called CAFLOD, which is basically simulating the flooding events. So once we know the different climate projections that we are going to use, that is being used by the CAFLOD model, which is basically a model. The methodologies are highlighted here, and the model name is here. So CAFLOD model is actually a model developed using cellular automata by the Center for Water Systems. Then we come here, the hybrid model that we are developing. We call it the resource allocation model, and which will take the input from the CAFLOD model for its decision making. Right. We also have a traffic model. How does the traffic model come in here? Because if we know where the regions are flooded, right? So the CAFLOD model can feed to the traffic flow model which roads can be flooded, right? And you can, I think, use ArcGIS to see which roads are being flooded and things like that. And using the agent-based model, which we have developed using Sumo, you can actually see traffic stopping, or because the water depth has increased, traffic's going slow and so on and so forth. And why is it important? Because some of this input will also come to our hybrid model, because if I am a decision maker and I want to see that if the area is flooded, then I have got certain resources with me, right? I don't have infinite resources. Then what is the best way of dispatching the resources? That is what our work is, right? So to show the sequencing of operations in our work, we have the climate projection models and the SSP-RCPs, which inform a flood model. Again, we have not developed the flood model, right? Like climate projection models, is the climate scientists who are working on this. Then we have a flood model, which our Center for Water System is working on. And then we have our resource allocation model. The resource allocation model will take input from this output of the flood model to show which areas, which critical infrastructures are flooded in that area, right? I mean, AnyLogic has GIS integration, as you know, and we already know where the hospitals are, where the train stations are, where the, let's say, the power substations are. Then we can think about cascading effects of failure. What does it mean? Like I explained before, if it is a substation which has been flooded, then the substation itself will not be down. That is true, it will be down, but will also affect, let's say, hospital. It may affect the train station, the schools, and so forth. Some of them may have generators and all, but obviously the service level is going to. So using, let's say, knowledge graphs, it is basically what you see here is basically using graph theory, right? And Neo4j graph database. So basically, you can have each node and you can assign weights and to them and the linkages between them. So we can query if a node is affected. How do we know the node is affected? From the flood model, which gives us the location. We know it is affected. Then we query the knowledge graph to see which other locations are affected by it. We get the output, and by that we know the overall situation of the network. Then as a decision maker, this is the AnyLogic model. I have certain tasks, I have certain resources, and I have certain tasks, right? And I can then take a decision by running the computer simulation, right? Once I know the cascading effects, where it is going to affect, and also what resources I have, I can run different computer simulations to see what is the best resource allocation, so that least number of people are affected from flooding or are brought to safety, or it could be that sending of water pumps, to the right areas, so that more people can travel freely, right? It all depends upon the stakeholders what they want, but this is the idea. And again, this feeds back to the there is also digital twin, but later on version of it, because what happens is that with floods and all, there are now so there are two things. One is the climate projection model. It is obviously about the future, right? We are trying to simulate 10, 20, 50, 100 years in the future. But also, this is proactive planning. There is also reactive planning. For reactive planning, what we mean that the flood gauges in Torbay area give us data, right? And we are already acquiring that data. So we know if there is rainfall, which areas are flooded. It's like a digital twin for reactive planning. So this model can also be used, one deliverable, as a digital twin for for reactive planning as well. So so this is how I guess I think gives a good picture of how different elements are linked together. I think I have only a couple of minutes left of my 45 minutes. So, and we have a visualization dashboard to be created now. So in summary then, what I want to say is that, yes, computer simulations are a good example of e-science applications. If you are able to use grid computing or cloud computing or HPC computing, weave them together in a network, you need good applications, right? To be able to take advantage of that. So simulations, because they are compute intensive, are a good applications because you get the answers quicker, which may enable decision makers to run even more scenarios and so on and so forth. But for e-science, obviously, what you also require is an underlying network of where people are working together, and it used to be this e-infrastructure. This term is now not heard that much more. Same as grid computing, because cloud computing and more ubiquitous computing has taken over that, right? But in e-science community, e-infrastructures did help in collaborative research, and modeling and simulation community did benefit from the use of this. So e-infrastructure can be an enabler for multidisciplinary, obviously, because if there are, you are able to send information because of the underlying compute networks, and also to some extent interdisciplinary research, where you are using interdisciplinary research in modeling and simulation, okay, where you are sending IEEE 1516 standard to communicate with different models, which may be belonging to different domains, and using that infrastructure. So it is possible. But if we want to shift from, multidisciplinary to inter and transdisciplinary, then use of hybrid modeling approaches is important, right? It is not only the compute infrastructure, e-infrastructure, that will enable e-science that we know, right? It has to be the working together of researchers and looking each with knowledge of their own disciplines, framework, methodologies, and approaches, yeah, and then trying to work in order to create these kind of very strong linkages between disciplines, right? And hybrid modeling approach is one way to do that, and we feel that RC is a good work towards hybrid modeling for transdisciplinary science. So I'd like to acknowledge finally the research team who have been working on these two projects, Ultimate and RC. They are from the Center for Water System. Otto Chen is from the University of Exeter Business School, part of it, and is a research fellow. And he developed the ultimate model, which I showed, the hybrid simulation model. The other thing, since I've had the opportunity to speak, and because obviously Germany is not too far, we are holding what is the 12th edition of the simulation workshop in the University of Exeter. If you'd like to come and present, then the dates are already set, 31st March to 2nd April 2025. So yeah, it's an early warning, but good to be prepared, right? The call for papers will be sometime in April. This will be the 24th year actually. It's a biennial conference. So yeah. And this is to the UK Operations Research Community, Modeling and Simulation Community. This is the equivalent, UK equivalent of the Winter Simulation Conference that we have, right? And there is going to be a special issue from the Journal of Simulation from this as well. And otherwise as well, please free. I know some of the work that, because I work with colleagues, with your colleagues, so some of the work, maybe simulation related work, could be a good fit for the Journal of Simulation, and I'm a co-editor for this. So feel free, if you want to know about the scope of the journal and all, you can feel free to email me as well. So with that, thank you very much for listening to my presentation.
Yeah, from our side, thanks a lot, Navonil, for taking your time and explaining like all this complexity. I understand you have deal with all holistic approach of like approaching the problems. So this will be like the official end of this part, public lecture. So I'll take it just pause